Hi, I'm Dr. Teeple, and welcome to another video today. And today we're going to be talking about something relevant this year in 2020, and it's about pandemics and the coronavirus, and also what I'm going to call the small world phenomenon. As we know, apparently this virus has spread within a month, so we do live in a small world, and I'm going to show you that in a short example at first, and then we're going to um, do a quick mathematical um, model that can show us when uh, to declare a pandemic from a smaller outbreak um, in a smaller area of the world. Um, so how can we model that? Well, one way is to model a social network. In this case, I'm just going to model it as a one-dimensional lattice that's um, has um, a periodic boundary condition, but that doesn't really matter um, because you could just take uh, uh, a limit of a large number of people, and it would just be a straight line. But we're going to model it so that each node is a person. So there's going to be L lattice sites, which will represent the people, and they'll have K nearest connections. So those could be your friends if you have K close friends. So those would be people that you're in contact with most of the time, or if you were, or if they're, in the case of a lockdown, there would be your roommates, or your family, or the people that you choose to stay um, in physical contact with. So so they would be the people that you are in quarantine with, or that you aren't social distanced from. Um, so there would be up to K of them. So we call those nearest connections, or they can be next to nearest connections. So those that are, um, they could have a weaker transmissibility of the virus to you, um, and we'll model that later on. Um, but so we model it like this with these bonds that go from a nearest neighbor to a more distant neighbor. But then there's also going to be some shortcuts, and these would be some long distance friends, say from a different city or a different part of the globe, that you socially distance from. You probably only see if there isn't a pandemic, or you just see only if you do long distance travel. Um, so these are shortcuts modeled by these lines, and there's going to be a probability phi of them per every bond. Um, um, that's not a shortcut. So those will be called the travelers, and there's going to be, on average of them, L times K times phi of them. Then, since it's a probability per connection, and there's going to be L times K of them, since there's K nearest neighbors per person. So we're going to look at a continuum limit of this, and then what we're going to do is we want to find the number of groups of people, and to see also what the average distance between a person is, to see how connected we are, as an example, and see how really small this world is. So let's just look at a person at, say, person X, and we're going to say that they interact with our nearest neighbors. So they're quarantined with our people. But say one of those persons, or no, say that person X and all those other people um, can travel, or even if this was just say even Facebook friends, in general. This is a general thing. It doesn't have to apply to a pandemic. You know, their friends long distance to these people, and then they have our um, uh, um, groups of friends, in quarantine as well, but then they travel or know somebody if it was Facebook friends, and then they um, are over here in the world and so on, with all these jumps and leaps. Um, and so we want to know the number of these clusters, and but we also want to know the number of gaps, so the number of non-infected people, and so, this function mu is just going to be the number of points or people that are not in this infected neighborhood. Um, and then, nu is going to be the average density of these gaps, so the non-infected um, um, clusters. So that's also equal to the um, of infected clusters too, um, um, since it has periodic boundary conditions. But and then all of these numbers are averaged over all possible random graphs, because we don't know exactly who's connected to who, so we just want to average and do a full statistical average over all possible friendships and connections of everybody in the world. And so we do that, and then what you can do is you can do a differential equation for nu as a function of how many people are close friends or are in quarantine with each other, and same thing for mu. I won't get into the details of it, but if you take the ratio of these two, you can easily solve for what nu is, so what the number of infected clusters are. And if you define a characteristic length, which is just 1 over k times phi, that has the units of length, you can get asymptotically in the continuum limit for large L that it just is this exponential function for mu, that the number of non-infected people, or the number of people who don't know you on Facebook or whatever, if it was just a social network, it follows this exponential function. And as you can see, as the more and more people you are quarantined with or interact with or know, it the less and less people there are who you don't know, or the less and less people there are who aren't infected. So it kind of looks like it starts out midway, and then it's an exponential decrease. So as you can see, that's why the number of infections is an exponential increase. What is the average person-to-person separation? This is just, I mentioned the 6 degrees of separation. So you can do that. You just have to integrate from 0 to the probability that everybody gets infected, but where weighted by the distance between people, and that gives you the average person-to-person separation. So you get this result. But if you want to have a 1 over e cutoff, then you get that the value for phi gives that it's about 6 long-distance friendships. So everybody's a friend of a friend of a friend of a friend of a friend. Or for the world for a pandemic to spread, it only takes 6. You only have to spit on somebody, and then them to spit on somebody, and then you only have to do that 6 times, and everybody has to do that 6 times, and so on. So back to the propagation of disease then. we can go back to this model, but I'll generalize it even more. So the sites don't all have to be occupied by people, but if they are, we're also going to assign the susceptibility of that individual to a disease. So I know the models that they do now are called the, like there's the Q, I, R, and S, or it's a different order. I think it's NIRS or SNIRQ models, right? It's quarantine immune response, um, um, something susceptibility models, but they aren't as rigorous. But they do take into account um, uh, it's more of a gas model than a lattice model, but it could be both. But it does take into this account. But we'll also assign the bonds between these sites, the transmissibility, there we go, of the disease to each of the bonds between the people, because that can be a variable. And then, as I said, not all the sites are occupied, so there'll be a fraction p of them that are occupied, and it'll be any random lattice in d dimensions. And we'll represent, well, I'm just going to use p naught of n as the probability that a given chosen site is in a cluster of size n. But p of n will be the probability that any randomly chosen site is in a cluster of size n. So a cluster size distribution is proportional to p of n over n, because you don't care about the number, the size of the cluster. We're going to look at the generating function because it's a little easier to compute. So if you sum from n equals 0 to infinity of p naught of n to z to the n, because you can actually compute, and I'll leave it as an exercise, that the probability that our given chosen site is in a cluster of size n is npq to the n minus 1 times 1 minus q squared, where q is 1 minus p all to the k. And then when you plug that in, you just work it out. You get 1 minus p plus pz times 1 minus q squared over 1 minus qz all squared. So with that, you can then find the mean outbreak size, and that's just going to be the generating function its derivative with respect to z evaluated at 1. And that can be found by a recursion equation. I didn't have room on the blackboard, but you can always read it in a reference that I showed you. And evaluating it, you get this result. And you notice that it diverges at a certain value of p. And it depends on the value of phi, which is the probability that somebody is traveling across a border. So an international traveler. And so there's going to be a pandemic at a certain critical finite value of p equals pc when the average outbreak size goes to infinity. So that means the whole globe is now spread. So it's spread across the whole globe. So when you solve for this denominator to go to 0, you get phi is equal to 1 minus pc to the k over 2k pc times 2 minus 1 minus pc to the k. When you look near the critical point, you find that the outbreak size diverges as 1 over pc minus p, So the critical exponent of that phase transition, the pandemic phase transition, is equal to 1. So that's just something interesting for this model. Um, yeah, so that's a topic today. Yeah, so since it depends on phi, it's good to close the borders. I know Trudeau and and even Trump, kind of failed on doing that. But oh well. um, yeah, let's hope there's not a second wave of this. But yeah, thank you for watching, and that was great.